is Talon Johnson, and I'm a PhD student in the math department, and the title of the project is Sparse Sampling and Fully 3D Fast Total Variation-Based Imaging Reconstruction for Chemical Shift Imaging and Magnetic Resonance Spectroscopy. Getting into it, chemical shift imaging is a technique in which we obtain an image of the chemical metabolites through the spectral distribution that are present in the brain that help identify brain tumors and other brain diseases in the early stages. However, a flaw of this technique is that it could take up to 20 to 45 minutes to obtain the imaging data, which can result in a patient's discomfort. Additionally, hardware limitations prevent us from storing all this information. So we propose a new compressed sensing technique to help speed up this data acquisition through compressed measurements. And this technique is known as 3D Direct. But what is compressed sensing? Well, you can think of compressed sensing. It's a technique. It is a technique that exploits the sparsity of a signal, in our case, an image, in its natural domain or in some other transformation domain. And from those domains, we subsample from that, and we take those measurements, which the subsampling we call a mask, and we use those measurements, those fewer measurements, to reconstruct the image and the desired image that we want without that much loss of granularity. In our case, we're going to use the 3D Direct in order to get the chemical shift maps of these four protons, alanine, formic acid, lactate, and bicarbonate, using two sampling scheme patterns, radial line pattern and the center weight pattern. Going into the 3D Direct, the 3D Direct is an optimization problem, and more strictly a minimization problem, which we minimize the total variation of our image X subjected to this constraint AX minus B, where A is our sparsifying linear transformation, or the mask, and B is the observation measurements. T is the total variation of our image, which is defined as the summation of the square roots of the squares of the discrete gradients. And we solve this problem using methods, mathematical methods such as conjugate gradient method and Newton's method. From there, we use 3D Direct in order to try to reconstruct the imaging map for chemicals. And as a result, we use two things to evaluate the quality of reconstruction, and that is the structural index, the structural similarity index, and the normalized mean square error term. And from what we can see is that if we sample, A is our true image, and B through D is subsampling scheme using radial lines going from 5, 3, 2 respectively, and E through G is the subsampling scheme using the center weight method going from 20%, 16.8%, and 11%. And from our results, we notice that as long as we sample at least 16%, we get a nice reconstruction. We get some nice reconstruction accuracy from my normalized root mean square error term. Additionally, if we sample at least 16% or more, we can see that the structural integrity of an image that we reconstruct is very similar to what the ground truth looks like. So that is to say that it turns out that the method that we use, 3D Direct, is a very feasible method for reconstruction using sparse data measurements. And for future work, we want to try to create an algorithm that simultaneously deconvolves compressed and convoluted imaging data. Thank you. I thank you for listening, and here are my references. Thank you.